Okay, so a natural question is, we've got these Gaussian integers, very simple, just integer combinations of 1 and I, and we have this idea of Gaussian primes, which is close to being like ordinary primes, but a little bit different. And then the natural question is, does the fundamental theorem of arithmetic hold? So it's easy to see that every Gaussian integer has a factorization into Gaussian primes. All right. So if alpha is not a prime, then we can write it as a combination of two other Gaussian integers. And by the assumptions, this is where Q, the quadrants of beta, and the quadrants of gamma is less than the quadrants of alpha. Well, in that case, then we can continue. So we factor it, and if we look at the constituents, and if they're not primes, then we write them as products of primes. And we can continue until all factors are Gaussian primes. Because the quadrants is always a positive integer. Because the quadrants is a positive integer. And it must eventually terminate because there's only a finite number of positive integers less than any given value. So this process must terminate. All right, so there certainly is factorization, but is it unique? That turned out to be an important question. So the question is the factorization unique? Is it possible for a number to be a product of Gaussian primes in two quite different ways? Well, it turns out that the factorization is unique. That's the answer. And the argument depends on some essentially geometrical kind of an argument. In fact, it depends on, as it does for the standard theory over the integers, it depends on the division property in the Gaussian integers. And so that's sort of the Euclidean property of division. And what is that? That's that for any alpha and beta are non-zero in our Gaussian integers, if we divide one by the other, then suppose we're dividing alpha by beta. Okay. When we divide one number, try to divide one number by another in the integers, 27 divided by 4, we get 27 equals some multiple of 4, 6 times 4 plus a remainder of 3. Okay. And the crucial thing is that the remainder is smaller than the number you're dividing by. And that's a very, very fundamental property of division in the integers, that prominently discovered and studied by the ancient Greeks. And fortunately, the same property holds here. But we have to state things a little bit differently. So we say that if we have two Gaussian integers, alpha and beta, then we can write alpha equals mu beta plus rho, where the size of rho is less than the size of the number we're dividing by. That's the analog in this setting of the fact that the remainder, when you divide by 4, has to be less than 4. Okay, and why is this true? So here's the reason. So suppose that beta, we're working in the complex plane here. Here is beta, and here's I times beta. Okay, we have to know that when you multiply by I, the complex number rotates by a quarter turn and has the same size. So these will be perpendicular and they form a square. In fact, if we look at all multiples of beta, we get some square lattice in the plane. So these are all multiples, integer multiples of beta and I beta. And if we have some number alpha somewhere, then it's in one of these squares. Okay, and that means there's a nearest point in this lattice to alpha. So let's suppose that this is the nearest multiple of beta and I beta to alpha. Let's call it mu beta. So if it's a multiple of beta, it's mu times beta for some Gaussian integer mu. And this difference will be rho. That's basically what we're saying, that alpha is equal to mu beta plus some error, which is rho. So here's this vector rho. Now if we go back to the origin, which is over here in our picture, and we have a look at what rho is, okay, rho is going to be over here in this picture here. We want to convince ourselves that this rho vector is actually of quadrants less than beta. That's the statement. That this difference is smaller in size than beta is. We can see that by observing that this rho has to be in the square here, where this is beta over 2. And this is I beta over 2. And so the quadrants of rho, being inside this square, it will be less than or equal to the maximum possible value of the quadrants in that square, which will be this quadrants of beta plus I beta over 2. This is the point. Beta plus I beta over 2. And by the multiplicative property of the quadrants, this is the quadrants of beta times the quadrants of 1 plus I over 2. And what is the quadrants of 1 plus I over 2? Well, it's that times its complex conjugate. So it's 1 plus I times 1 minus I over 4. That'll be 2 over 4, or 1/2. So this will be beta over 2. Oh, sorry, it'll be quadrants of beta over 2, sorry. And that will be less than the quadrants of beta. That's the crucial inequality, that the quadrants of rho is ultimately less than the quadrants of beta. So that makes the division algorithm work. And then if you go back to the Euclidean proof of unique factorization, Euclid's proof of unique factorization basically employs this property crucially for the unique factorization. So then you can take that proof and just adapt it to this situation, and it works. So the Euclidean proof essentially works here. Once we have this crucial division property. So yes, it's true that in the Gaussian integers, there is unique factorization into primes. So people thought, well, that's great. This kind of arithmetic with these kinds of numbers is much like what we're used to. But however, there was a shock in store. Okay, so there was a surprise. The surprise is that it's not always so simple. The story is not always so simple. In particular, if we look at the integers adjoined square root of minus 5. So here what we're doing is we're taking the equation x squared plus 5 equals 0. We're looking for solutions to that equation. If you're happy with complex numbers, you would say, well, that's the square root of minus 5, although actually there's two square root of minus 5s, square root of 5 times I and square root of 5 times minus I. But another way of saying it is just to say, well, that it's the integers where you augment something with a symbol r to the minus 5, r sub minus 5, where r sub minus 5 happens to have the property that when you square it, you get minus 5. So we're talking about things with the form a plus b r sub minus 5, where a and b are integers. So this is a lot like the Gaussian integers. Instead of having a square root of minus 1, we're talking about a square root of minus 5. In this case, the quadrants of an alpha, something like this one here, will be a plus b r. Let me just write r for r sub minus 5. So a plus br times a minus br. And that will be a squared plus 5b squared. So what do primes look like? Well, primes in this setting, in integers with r sub minus 5, include, well, 2. 2 is a prime because the quadrants of 2 is 4. 3 is a prime because the quadrants of 3 is 9. 1 plus r because the quadrants of 1 plus r is 6. And 1 minus r because the quadrants of 1 minus r equals 6. The quadrants of numbers, there's not a lot of possibilities for the quadrants of small numbers. If you're talking about things of the form a squared plus 5b squared. So the smallest possible quadrants would be 1. And then the next smallest possible quadrants would be 4. And the next possible quadrants would be 4 plus 5, which would be 9. Squared there, 9, 14. There are not a lot of possibilities. So that there's, if you're trying to factor some number like 3 in terms of two smaller things whose quadrants are smaller than 9, there aren't a lot of possibilities for things which are smaller than 9 in quadrants. So these are all primes. But then 6 is 2 times 3, but it's also equal to 1 plus r times 1 minus r. So in this strange kind of ring, which includes a square root of minus 5, we see that the number 6 can be factored into primes, but in two quite different ways. One using the primes 2 and 3, and the other is using the primes 1 plus r and 1 minus r. So unique factorization does not work. This was a bit of a shock, and it was actually a source of errors. So there were a few people who tried to prove Fermat's last theorem using kinds of square roots and cube roots and things like that, and they didn't take into consideration that this kind of unique factorization doesn't necessarily work, and so there were some actual errors when people just assumed that this all automatically worked when it doesn't always work. Okay. So a couple of people pondered this, and the natural question is, okay, so when does it work and when doesn't it work? That's an important question. Even if you're just working with relatively small algebraic integers, where you're adjoining a square root of something. Okay? It works for -1. It works if you take the square root of 2. It doesn't work if you take the square root of -5. What happens if you take the square root of 349? Does unique factorization work or not? That's quite a challenging problem that generated a lot of interest. But another kind of question that naturally arose is, all right, if unique factorization doesn't work, can we fix things? Can we rethink things so that somehow unique factorization is recovered? And there are two names associated with this work. One is Kummer, and then Dedekind, who realized that there were some kinds of ideal numbers. That was sort of Kummer's thinking. And then Dedekind replaced that notion with the notion of ideals. And with these ideas from ring theory, they were able to recover unique factorization. So unique factorization was recovered, at least in some these sort of quadratic situations, was recovered by replacing algebraic numbers with, well, essentially sort of ideals. So the arithmetic of numbers became replaced with the arithmetic of ideals, and I want to just tell you a little bit about that. All right, so a very quick introduction to the idea of ideals in a ring. And to make life simple, let's just go back to the integers. Okay, so here are our integers. Let's suppose we're interested in a particular number, say 3. Well, associated to 3, the number 3, we can associate an idea which is seemingly perhaps a little bit more complicated. The idea of a property, the property of being a multiple of 3. All right, so let's call that property, say, P sub 3. So we'll say that 6 has the property P sub 3. This means that 6 is a multiple of 3. Now, Dedekind didn't think about it this way. He thought in terms of infinite sets. So he thought rather about the set 3z, which is in some sense sort of equivalent to this property. This is an infinite set, and this is a property, so I prefer to think about things in terms of properties, which is more sort of finite in computation. So Dedekind would have said, let's consider all the multiples of 3. And not just positive ones, but also negative ones as well. And that whole set is what he called an ideal. So this set, which you might call 3z, this is an ideal. And what makes it an ideal? Two things. First of all, that if A and B have the property, then A plus B has the property. And secondly, that if A has the property and C is arbitrary, so C is an arbitrary element, then A times C has the property. So in other words, the property is closed under addition, and it's closed under multiplication by anything in the ring. Okay? So Dedekind says, let's call that an ideal. Okay, that's good. And a particular example, if R is a ring and A is an element of the ring, then we could define P sub A to be the property of being a multiple of A. In Dedekind's language, this would be A times R. So A times R, or sometimes A, is just the set of all things of the form A times X, where X is in R. If you have any element in a ring, you just multiply it by all possible elements, you get some set. And then that set is an ideal. This is called a principal ideal. Now, in the integers, all ideals are principal. In Z, or the integers, all ideals are principal. Also, in the Gaussian integers, that's also true. But it turns out that there are examples of rings where there are ideals which are not principal. In particular, the root minus 5 example that we talked about has an ideal which is not principal. But the integers adjoined root of minus 5 has non-principal ideals. So, for example, let me try to draw a picture, maybe not the usual kind of picture, but this is not a picture of the complex numbers. This is a picture where we have 0 here, 1 here, 2 here, 3 here, and here is R. Okay? R is what I'm calling R sub minus 5. You can think of that, if you like, as a square root of minus 5. We're just thinking this as being, this is our integers adjoined R sub minus 5. So we can think of this one here, for let's say this one here. This would be 3 plus 2R. And what is a non-principal ideal? So suppose we take all multiples of 2 and multiples of 1 plus R. We get this nice checkerboard pattern. All right, so in blue here, we see the ideal, which is the principal ideal of 2 plus the principal ideal of R plus what? Or 1 plus R, let's say. This is a non-principal ideal. All right, so there's lots of interesting questions. For example, when does such a ring coming from, say, a quadratic extension of the integers have non-principal ideals? And if so, how many non-principal ideals are there? Dedekind was able to show that with this language of ideals, you could do arithmetic with ideals. Okay, there was an arithmetic with ideals. So for example, by the sum of two ideals, we just mean all the things that we can get by taking one element from this ideal and another element of this ideal and adding them. We can multiply two ideals. We can take the difference of two ideals. And with this sort of ideal arithmetic, the unique factorization can be made to work. And with this unique factorization is recovered. You might say, well, why is this called an ideal? Well, Kummer's idea was that if you take some situation like this, in some sense there's something at infinity for which this is all just multiples of that thing at infinity. So sort of Kummer's kind of idea that there should be these ideal elements which are not actually in your ring, but nevertheless that generate such an ideal as all multiples in some sense. But Dedekind then went a little further and said, forget about the things at infinity, let's just look at the sets themselves and call them ideals. And this is a very important notion of ring theory, and ring theory went on to blossom in the 19th and then 20th centuries, became a very big subject with lots of interesting things, and a huge amount of work has gone into studying the arithmetic of these algebraic extensions, where we take the integers or the rational numbers, and we make some algebraic extension, and then try to do arithmetic in this algebraic extension and see what happens.